Hi, my name is Henrik, and today I'd like to present our results from an application of modified Shewhart chart used for fault detection in a district heating system. So, the big issue we have in the world is too much energy consumption and then too much CO2 emissions, and heating plays a big part of this. That heating consumption is a great part of the total heat consumption in the world. So we want to reduce it, increase the efficiency of the heating supply. In Denmark, a lot of the heat is supplied by district heating, so that is which is then the focus of this paper. So we want to improve the efficiency of this district heating system to lower the CO2 emissions and energy use. One interesting thing about this is that it's estimated that 40% of energy use in district heating system is caused by faults. So it's therefore important to then detect these faults, and this can be done via continuous commissioning in energy systems. So making sure everything is working while it's in use. Right now, reactive maintenance is used a lot, and that is very inefficient, and also plant maintenance. So we want to enable real-time monitoring or like proactive maintenance of the system, and this is not done in Denmark. So the types of faults that happen in district heating systems could be misconfiguration, sensor faults, and wear and tear of the systems. Sensor faults could be categorized more in data validation aspect of the system. And these again could impact occupant discomfort, energy waste, and then again, because of energy waste, financial consequences. So fault detection methods are able to alleviate these problems that we face in like energy waste and discomfort by enabling proactive maintenance. And they do this by real-time monitoring of the systems, and then they can detect the faults via some method for fault detection, and then they can identify the cause and location of the faults via diagnosing the issue. We can then focus attention on those areas and send out a maintenance crew to like figure out what is wrong with the system and then fix it. This improves the time allocation of the maintenance crew, and then which then in turn lowers the expenditure, and then we can reduce the energy waste via this early detection instead of it being there for a long time. So now we've moved on from that. The next part is looking at what is also special about district heating. So here it's very important to also see that district heating system is a very complex system, and it changes throughout the year what is normal operation. So the context is very important, where you look at the winter or the summer. As seen on this picture of a dog, context is very important. So for example, 8 megawatt hours of energy usage in winter is normal, but not in summer. And this is kind of an essential aspect that must be included in the models that are created. It's not just the consumption, but also other aspects that change throughout the year or change throughout the day as well. So the method that we choose must be able to take this into consideration. Now that we've talked about the context thing, there's also some other things that we are looking for when choosing the method that we want to use for fault detection. So one of the things is that it's scalable, so you can scale it up to many methods or to other systems or subsystems. And other ways that it's easy to implement, that it doesn't take that much change to perhaps apply it from a subsystem or to consumers, perhaps like consumer data. And it already also uses already installed infrastructure, and then of course we consider the contextuality of the system. So the method chosen is Shewhart chart, but as say that a Shewhart chart works on a very like static control limits, where you have this process variable. You can see this is the measurements, and when it's outside these static limits, it's out of control, and then there's detected a fault. But I just said that we need some dynamic control limits, because these limits change throughout the year. In the winter, this is perhaps what is normal, but in summer it's a wider gap that's allowed or something like that. So how do we do this? Is that we put in like we use a so-called contextual variable to create dynamic control limits, and this could be based on outside temperature, that we create like specific control limits for all times where the outside temperature is at like a certain temperature. So I'll talk about the intervals later. So first, how to determine the contextual variable. So here's for the system a cross-correlation chart. That is what you can use to identify what variable you want to use as a contextual variable. So here you can see outdoor temperature is also an external variable, and it's very interesting to use that as a contextual variable. So we base the limits upon the, for example, outdoor temperature, and you can see there's a high negative correlation between a lot of these sensors, which means that it's quite good to use, and also some positive correlation between some of them. So it's a good correlation between that and then these individual sensors. So it's a good pick as a sensor. Now that the contextual variable has been determined, the next part is looking at training the model with the training data, of course. So what we see here is the contextual variable with its measurements along with whatever sensor it's highly correlated with. And then we create different bins of the contextual variable measured from the minimum to the maximum value with a certain size. You can see here we created 2 here, and then we sort the variables into these boxes according to which interval they correspond to. And then for each of these matrices, we can then calculate the control limits as seen before on the previous slide. And then based on this is what is used then to use for the testing of data, where you then plot the testing data and see whatever is within or outside these limits, but they're still sorted into the proper bins for testing with the new testing data. So the case study is a district heating substation. As you can see, the general setup here is with some consumers and some few pumps and valves to control it, and then we have measurements of pressure, temperature, and flow at different places at the substation. The main thing here is what we want to test is that there is a known fault in the system that was given in the forward energy, like the energy going to the consumers. There was a misconfiguration of the calculation, as you can see here. There was an underestimation of what the forward energy was. So you can see the real corrected data is the blue line, and the orange is what was actually calculated, faulty data. And you can see the residual error here. And now for the results of the method with the known fault as a small example, where you can see this is like a chart you can produce with this method with all the temperature intervals, and then the measured forward energy. And the red ones are based on the training data, the control limits, and all the blue circles are from the testing data. So you can see it's all shifted down from the mean, and that is because as we just know, the measured value was lower than it should have been. Like the misconfiguration resulted in a lower calculation of forward energy. So it fits with the result, and it's able to take the fault. So another interesting note here is just for a different sensor, but we want to look at this plot instead. But it's interesting to point out that the method is kind of able to predict the value as of the system, so it's able to properly capture the essence of the system, you could say. Yeah. To conclude, the method developed was able to take the known faults with some change and thought behind the control limits. The method is better at capturing the seasonality of process variables compared to normal Shewhart charts, and it's easy to implement and very scalable. One problem is that it creates a plethora of charts, so there needs to be a way to summarize the faults detected for the different work. So that leads me to future work. So one thing is that we have one method now detecting, but the goal would be to implement multiple methods for fault detection. And also a way to determine the severity of the faults, as there are so many faults detected. So we can rule out some of them as not worth it or feasible to look at them all. And then also perhaps validating this method even more by looking at more known faults in the system. Thank you. That was all. If you have any questions, please ask them now.